discussing the associative memory networks. We have seen the pattern association, right? So we have seen how the patterns get associated and stored in the memory. So essentially auto, hetero associations. Also, we have discussed in the previous class bidirectional associative memory, where two different patterns X and Y or S and T gets associated and stored in the memory. Not only one set of patterns, but there are ways there is a way where you can store multiple patterns. So that means X1, Y1, X2, Y2, X3, Y3, and so on. So once you store these patterns, you can retrieve them in either of the direction. That means providing X as a stimulus, get Y as the response, or you provide Y as the stimulus and get the X as the response. So when you have when you provide X as the input and getting the Y as the response, we are supposed to use the weight matrix W as the memory. When you are providing Y as the stimulus and getting the X as the response, we are supposed to use the W transpose as the memory. And not only that, we said you can even try with the noisy patterns as well. Okay, so this is what we discussed in the pattern association. Next, we continue with our discussion with next set of network called Hopfield networks. Okay, so Hopfield network is number one, it is an iterative network. I hope you guys remember that in the very beginning of the pattern association, we talked about feed forward, similarly iterative, two varieties of approaches. So we are going to discuss today an iterative approach, which is Hopfield network, and either you call it as iterative or you can even call it as a recurrent network. Okay, you can call a recurrent network. Similarly, now what we are going to discuss is the auto-associative network. So we are going to store the patterns, not only one pattern, we can even store multiple patterns. So we can store the pattern and retrieve the same pattern. When we are retrieving it, obviously we can retrieve with a noisy as well. So it is an iterative or a recurrent network. Similarly, what we are going to discuss is the auto-associative network. And remember, the interesting aspect is that the network will not respond. Okay, the network will not respond to an input immediately. Okay, the network responds in asynchronous fashion. Okay, we will discuss what is asynchronous fashion. Okay, weights get updated in the asynchronous way, and so in fact the network is going to take some kind of iterations to converge. Okay, so the iterations happens or the convergence happens in the asynchronous fashion. Okay, we will discuss what do we mean by all this. Similarly, when you look at the architecture, it is essentially a fully connected network. Okay, so it is fully connected network, and remember the weights are symmetric in nature. Okay, we will discuss all these things. Okay, these are all the various properties of this particular Hopfield network. So the weights are symmetric in nature, and remember there are no self weights. Okay, so that means when you take the weight matrix, obviously the connection the connection matrix, when you take the weight matrix, the principal diagonal would be 0. Since it is a symmetric matrix, what do it mean? Means when you take the connection weight from Wij, that means ith node to the jth node, is equal to the connection weight of jth node to the ith node. And remember, when we say no self weights, that means Wii is equal to 0. So this is I is not equal to j. When I is equal to j, that means II is equal to the connection weight is 0. Okay. So now let us have a look at the network architecture, how it looks. Okay, there is. Okay, maybe I will take it to the next slide also. Anyway, look at the diagram. On the top, you have connections X, X1, X2, so on. So, and on the bottom, you have the Y connections, Y1, so on, Yn. Okay, maybe I will better take it to the next slide and keep it so that you will not have any kind of let us go to the next. How do you can see this? So this is how the network architecture of the Hopfield network, discrete Hopfield network looks. You can see your X1 to Xn. So this is the layer X and this is the layer Y. Okay, where you get the output. Okay, now if you notice, obviously there is input going as an going to the output nodes, the Y nodes, and you can see their connections also. And if you notice, the output from Y1 is going again. If you notice, Y1 is going again back, which is the feedback. Okay. And when it is going as an feedback, remember, it is going it as an input to the other nodes. Okay, you can notice that. Okay, so Y1 is going as an input to the other nodes for the next iteration. Remember, in the first iteration, when you submit the input, it moves, and the output goes as a feedback to the other nodes in the network for the next iteration. Okay, so that means whenever you are looking at the network, you can say that for a particular iteration, you can say that the net input at a particular node called Y, a particular jth node at the layer Y, okay, can be set that corresponding input, okay, plus sigma I is equal to 1 to n. You have n number of nodes, 1 to n Wi, and okay, I will write here. Otherwise, I'll write here. So net Yj is equal to xj plus sigma I is equal to 1 to n Yi into Wij. Okay, remember, this is for the cases where I is not equal to j. And if I is equal to j, there is no connection at all. So you can think that it as a 0. So that means what? Leaving the first iteration, for the next iteration, the net input, say take an example, you are at the node Y1. What is the input to that net input to the node? It is the X, that means X1, and the remaining nodes, that means Y2, Y3, so on, Yn. For the remaining nodes, whatever that output and corresponding the connection weights. I hope you guys are able to follow. Any doubts here?
No, sir.
Again, I repeat, for those if you have any kind of an ambiguity, imagine you are at, say, take an example, second node, Y2. For the Y2, what is the net input? The net input is the input that is coming, which is X2 node from X. And in addition, whatever the output of the remaining nodes in the Y layer. So what are the remaining nodes in the Y layer? Y1, Y3, Y4, and so on, Yn. And the corresponding connection weight. Now you look at this Y2, you see that Y2 is having the connection from Y1, W12, that is the connection weight. Are you able to see that? So similarly, Y2 is also having connection from, say, this is the ith node. It will have the connection from ith node. So this is Wi2. Similarly, it is having the connection from the nth node. So this is Win. So that connection weight and the output, corresponding output at that node. So the Y node. So each node is getting the input not only from the X layer, but remember it is also getting the input from the Y layer. I hope you guys now are able to follow. So this is how your net input to the node is getting calculated, and the network takes either binary or bipolar. Okay. So the architecture, if you look at, it is essentially single layer in the sense that, here if you see the layer X, it is only just sending the signal, and your calculations are happening at the Y layer, and that's the reason why you regard this as the single layer. And since there is a feedback coming from the Y nodes to the next iteration as an input, it is called single layer feedback network. Okay, this is single layer feedback networks. I hope you guys are able to follow. So that means, if you, again I repeat, that means each node or each unit is receiving input from external signal. What is the external signal here? That is the X, and it is receiving the signals from other units in Y layer. Okay, so as I've said, Y2 is getting the input from the external signal, which is X2, and in addition, it is also receiving the inputs from the other units in the Y layer. And obviously, you are going to look at the corresponding connection rates. And the point is, another important functionality is of this particular network is, at any given instant of time. So at any given time, only one node. So only one node gets activation and updation. Okay. So when I say this statement, if you look at Y1 to Yn, there are n number of nodes. So far, when you look at the backpropagation network or any other network, you are calculating the net inputs, applying the activations, and proceeding in the forward direction. But look at this particular network. At any given instant of time, you would be focusing on one of the node in the Y layer, in the sense that you have n number of nodes in the Y layer, Y1 to Yn. At any given instant of time, you will pick only one node. And remember that picking up would go in a random fashion. Okay. So that means I can choose, at a first instant, I can choose Y2 node. I can choose next Y3 node. Maybe I can choose next Y5 node, then Y1 node, and say next Y4 node. Imagine you have 5 nodes in the, just for the sake of simplicity, I'm taking 5 nodes. If you have 5 nodes, so I'm taking the order of activation, order of updation is through this particular order. If you want, you can even choose, no sir, I want to choose a different order, say Y3, Y2, then Y5, Y4, and Y1. That's fine. So, but at any given instant of time, your activation and output verification and these calculations goes only one unit at any given instant of time at a random order. And that's the reason why the updation or this particular network is also regarded as asynchronous updates. Okay. Are you able to follow?
Yes, sir.
So far, any doubts? Let us take the algorithm, how this works, and see, proceed. This is your Hopfield association algorithm. So you have M unit Hopfield network, and you are giving an input pattern x1, x2, so on, xm. Then for that, first step is you initialize the activations. This is the first step. For the given input, what is the activation with the input signal? Then update the activations of the units in the random order. That is what I have said in the previous slide. So you have m number of nodes, you choose any order, okay, and perform the following steps. So imagine you have chosen jth unit. For that jth unit, first you check the net input. And obviously, when you look at the net input, this is the external signal. And what is this? This is the input coming from Y layer. That's what we discussed in the previous slide. So the jth unit is receiving the external signal from the jth node, and for I not equal to j, you are taking the remaining nodes output and their corresponding weights. So typically this is a kind of an Hebbian rule. Okay, this is a kind of an Hebbian rule. The kind of what is the updation, if you look at the activation, if you look at it, is a typically Hebbian rule. And then your activation, if you look at, so the network provides the activation. If your net input to the node is greater than 0, it is 1. Otherwise, the remaining condition. And remember, we are updating this only on one node. Okay, that means your jth node. Which is that node? Jth node. So once you update, once the activation of jth node is updated, then what happens? That updation is getting broadcast to the other nodes. That means Y1, Y2, Y3, so on, the remaining nodes, the m number of nodes in the network. Then what we do? We look for whether there is any convergence. If there is no convergence, we are going for the updation. Remember which unit we are going to update? Leaving the jth node, you may be picking the one of the remaining nodes in the network and go for the verification process. Okay. So this is what is the typical working of Hopfield neural network. So that means if you notice, What happens in the case of the network activation? I'm just writing again what the algorithm is doing. So it is asynchronous fashion. Of update. So it takes input pattern, input pattern is applied, then output is initialized for the first iteration, then the output, whatever that we initialize, the output initialized becomes new updated input, right? New updated input through feedback. Okay, that means what happening? You are submitting the input and you are initializing the output for that particular input. That means the auto association what we are doing. Then whatever that output we have initialized, that forms the input for the remaining units. Say take an example, you are updating a particular unit. For the rest of the units, this is the becoming the input. Okay, and goes on. So this particular process goes till network reaches an equilibrium. Okay, equilibrium means your network is able to capture the your auto association. Okay, so what we will do is maybe we will take one particular example and then see how actually the network is proceeding. So let me take one particular example and then we will proceed. So that you will be having a better clarity of how it is working. So imagine that you have an input vector like this. Okay, so the input vector is 1, 1, and 1 and minus 1. So you have a bipolar vector, and imagine if there are missing entries, okay, or noisy input at first and second components. Okay, that means this and this, right? So that are given as the input for testing. So that means then what will happen is your input becomes 0, 0, 1 and 0. Okay, this is for the input. Now anyway, first let us take the your initial vector, input vector, and say what would be the weight matrix. So the weight matrix of the memory, Hopfield network memory, is obviously your typical auto association where you are going to associate S transpose T. In this case, S transpose S. Okay, so 1, 1, 1 minus 1 into 1, 1, 1 minus 1. Okay, so what would be your weight matrix? What would be your weight matrix is 4 cross 4 weight matrix, W. Right?
It's not the same input in continuous 3 rows and -1, -1, -1, -1, 1 in the 4th one.
Yeah. Remember, as we have noted, we need to keep the principal diagonal as zeros. Okay. Because there is no self connection to this particular network. Okay. So 0, 1, 1 and minus 1, 1, 0, this is 1 and this is minus 1, this is 1, 1, 0, minus 1, this is minus 1, minus 1, minus 1 and 0. Okay. Is that okay? So this is the weight matrix. So this forms your memory. Now the point is, you are given the input. What is the input that is given is 1, 1, 1, 0. This is binary. Remember, we have created the weight matrix for a bipolar pattern, and we are taking the binary input, and wherein which we are considering the first two as the noisy inputs. Okay. So the point is, let us take the input vector as my input vector is 0, 0, 1, 0. And obviously, since it is the first iteration, your input is also initialized at the Y layer for the network. So Y is also 0, 0, 1, 0. Right. Now the point is, I have four neurons in the 4 units in the layer, Y layer. Which unit I am going to update? Imagine my my updating random order, the synchronous order is first Y1, then Y4, then it is Y3, and this is Y2. Okay, this is, imagine that this is my order. First node, then fourth node, then third node, and then second node. So now what I'm going to do is my choose Y1 unit for update. Okay. So when I take Y1 unit as an update mechanism, what is the net input to Y1? Net input to Y1 is X1, and the rest of the nodes, J is equal to 1 to 4. There are 4 units, 1 to 4 Yj into the weights, Wj1 transpose. So in the sense, X1 is what is the input? The input is 0, right? This is X1, this is X2, this is X3, and this is X4.
Sir?
Right? Yeah, please go ahead.
Sir, how we got that 0, 0, 0, 1, 1, minus 1? Like
Where?
Near W, sir. Where
This
you
one?
have written. Yes,
This
sir.
one.
Yes, sir.
Yeah, this is the weight matrix, right? I have written here the weight matrix calculation.
So, okay, we have multiplied these two matrices, right?
Yeah, that's all. Your outer products.
But it should be different, right? Like it should be 1, 1, 1, minus 1, and then like normal.
Yeah, that's what I have told. No, what is this I have written here? What is this?
No self connection.
Yeah. So there is no self connection, right? So when you don't have self connection, what happens? The principal diagonal elements becomes 0, right? Even the other day also we discussed, you have an auto-associative memory, all principal diagonal elements will have 0 because will become 0 because there is no self connection. Okay. So you submit the input vector. Okay, remember, okay, I have written here, this is not X1, this is X1, X1, X2, X3, X4. Okay. So now we are updating at Y1, only at Y1. So X1 is 0. X1 is 0. And the rest of the nodes, Okay, for the rest of the nodes, of course, even if you take we need not take first node, but imagine if you take it also, because anyway it is 0. So let us take entire bivector, which is 0 0 1 0, and your corresponding weight vector, that is wj1. What is wj1? Wj1 is this. Anyway, it is 1j. I am keeping it as a transpose. So you have 0 1 1 minus 1, this particular vector. Okay, so my entire y and w1j, okay, I'm writing it as wj1. Okay, so 0 1 1 minus 1. So this gives you 0 plus 1, that is 1. Okay, so when your net input is 1, you know what is the output. What is the output as per the activation? It is the output is also 1. So with output 1, how your y is going to get transformed? As 1 0 1 0. Next, I am going to choose as per the order 4th unit, y4 unit for update. So what is net y4? x4 plus summation the remaining. So j is equal to 1 to 4 your yj to wj1 transpose. So what is x4? x4 is 0. Look at x4. x4 is 0, and your y is 1 updated y 1 0 1 0, and you are going to consider the j1. What is the j1? Is this particular vector minus 1 minus 1 minus 1 and 0, right? So this gives you an output of this gives you an input of -2, and hence it fetches the output of 0. With that, your y is going to be the same 1 0 1 0. Are you able to follow? Any doubts?
Sir,
Yeah.
like where is the activation function return using which we are calculating the outputs?
In the algorithm, you notice?
Okay, sir. Okay, got it. And sir, how we came up with that order? Y1,
It's a
Y4.
random order. You see here, the algorithm says. That's what I said. Imagine if I don't give you the order, this is the order given in the problem. Y1, Y4, Y3, Y2. You choose any order. So my suggestion is, once the session is done, I would suggest you guys to check with the other order. Say, take an example, Y2, Y3, Y4, Y1. No issue. So choose Y2 unit first, then Y3 unit second, Y4 unit, then followed by Y1 unit, and see how the network is able to converge. Okay.
Okay.
So any doubts here, please ask. Net y4 we have done. X4, remember x4 comes from 0, and your y, the previously updated y, and the connection weights. Remember, we are looking for the 4th node connection weights. What are the 4th node connection weights? These are the 4th node connection weights. Similarly, once it is done, what is the next step? Can somebody tell me?
Go for Y3, net Y3.
Choose Y3. For Y3, what is the input from the external signal?
Like X3 will be there. Like
X3 is the 1, right? Plus X3 is 1, and X3 is 1. Yeah, yes, X3 is 1, and you have updated Y coming from net Y4. You see that this is the updated Y, right? So 1 0 1 0. This becomes 1 0 1 0 coming from here, and you are going to choose the weight vector that is the third vector, that is 1 1 0 minus 1. This is for y3. Okay, and see what is the output, and accordingly update the y, and tell me what is that you get. Okay, please net y3, and what is the y you get?
Net y3 is 2. Like y in is 2. Y net y input.
Okay,
And output will be it is greater than 0, so 1.
so what becomes to your y, updated y? You are updating the third one only, right? So it is becomes 1 0 1 0. Correct?
Yes, sir.
Then as per the order, we have to choose next 2. So y2. So net y2 with net y2, can you please guys tell me? So look at the input x2 is 0, and your updated y is here, and your weight vector is the second vector.
Sir, again y input is 2 for y2.
Okay, so you get positive output, so that becomes 1 1 1 0, right? So what is the input we have given? Our input is we have wanted to get the binary input, actually that is 1 1 1 0. We gave a distorted input, that is 0 0 1 0. We got 1 1 1 0 as the output. Okay, at the fourth iteration or the fourth step. Now typically what we generally do is we don't stop here. Again we take this, apply, what is the order? y1, y4, y3, y2. Okay, so apply y1 again. Then
So is
1
the
minute.
net y2
1 minute,
2?
1 minute, 1 minute. y1, y4, y3, and y2 order. Okay, and check whether finally again we are getting the same y or not. Okay, so we don't stop with one step iteration, though we are seeing the output. Okay, this is what we say, that it is actually only when in the next iteration also if we are getting the same, we say it's convergence. Okay, so tell me, yeah, somebody is asking something.
So net y2 shouldn't it be -2? Like x2 is 0, and then yj is 1 0 1 0, and then the w component is -1 -1 -1 1. So wouldn't that give -2 as net y2?
We are taking x to the second.
Yeah, I think you have to see the way we are calculating here. You did not follow. Yeah,
Okay.
what is the weight vector of the second unit? 1 0 1 -1, right?
Yes, sir, I got it. Okay.
Yeah. So now what I suggest you guys is to go back, since this once the session is done, so you do for the next iteration. Okay, so repeat this another iteration. Okay, this is one thing. Second thing is change the order. Right, so you change the order and see how the network is able to converge, whether it is able to converge in the same order or not. So see the order, you can even change like this. Okay, we said y2 in the reverse order, y2, y3, y4, and y1. Okay, because as we said, the network works with the random order fashion. Okay, and remember, I hope you have followed that every time we are updating or calculating for only one unit. Okay, not for all units. That is another thing which you need to remember. And another thing is, if you see, we have done for only one vector, So you can even try for multiple vectors, storing multiple vectors. So x1, x2, and x3, and so on. So you have some of the interesting problem in the book where you have the 3 vectors getting stored in the network. So please look at the problem number 14, okay, of your book, that gives you way that how multiple patterns can be stored with the Hopfield network, like x1, x2, x3, and you can retrieve the patterns. Okay. So please do that, and then we will connect again in the next class. Okay. So in fact, what we have discussed is for the discrete network. In the upcoming session, we will be connecting with the continuous bidirectional associative memory and the continuous Hopfield network. Okay. So that we will be discussing, and in addition to that, there are